Okay, differential equations. This is the 2012 AP Physics C, number 3. This is the one that has the distinction of having an average global score of only 2.7 out of 15 points. Let's see if we can do better than that. So we've got a ring, mass m, radius r. It's got a rotational inertia of mr squared. It's initially sliding on a frictionless surface. As shown above. At time 0, it encounters a surface with a coefficient of friction mu and velocity v sub 0 to the right, as shown above. At time t equals 0, oops, sorry, I just read that, and it begins sliding and rotating. After traveling a distance L, the ring begins rolling without sliding. So after here, it's like kind of rolling forward but sliding somewhat, and then finally here, like totally grips, and then it's rotating with no sliding. And express all answers, blah, blah, blah. Okay, I'm just going to say right here, rotating with no sliding, this means that there's kinetic friction. Here, that means that there's static friction, and the real key to this is when you are rotating with no sliding, that is when your velocity is equal to omega r. Right? That's not true here. If you're sliding and rotating, that means your omega r would be actually a little bit more than your v, right? Because some of your omega is not actually translating into rolling. So this is key. When you're rotating with no sliding, that needs to be true. All right. Part A, they want us to write a couple of differential equations. Part A, 1, using net force equals mass times acceleration. Well, the only force acting on this is the frictional force, which is in the opposite direction of motion. So that would be negative normal force times the coefficient of friction. That's equal to mass times acceleration, and they want a differential equation for v, so I'll replace that with dv dt. The m's cancel out, and I get dv dt is equal to negative mu g. All right, part 2 of that, they want me to do the same thing, but now with net torque is equal to I alpha, and the net torque is coming from friction, so that's mg mu times the radius. Force times radius gives me torque. It's at a 90-degree angle, so I don't need a sine theta. The rotational inertia is mr squared, and alpha is d omega dt. So the m's cancel, one of the r's cancel, and I get d theta dt is equal to, let's see, what do we have? G mu g over r. All right. This one's negative because the friction's slowing the hoop down, or the ring down, but the friction is increasing the angular velocity. Because when it was sliding, it didn't have any angular velocity here, right? And then it started to rotate. So its angular velocity started to increase, where its translational velocity started to decrease. All right, part B. Derive an expression for the magnitude of the linear velocity as a function of time and the angular velocity as a function of time. And they want the magnitudes of them. So it's kind of weird that they want the magnitude. I think I'm just going to do them as the functions. We'll see what it says in their scoring guide. So if I want a function for v as a function of t, then I need to solve this. So I'll separate my variables. That's going to be dv is equal to minus mu g dt, and that's just a constant, so that means v is equal to minus mu g t plus c. I'm going to use the condition to solve for c. I'm going to use that at time 0 the velocity is, time 0 is when it hits the friction patch, and its velocity when it hits is v sub 0. It's not 0, it's v sub 0. So that would give me v sub 0 is equal to minus, this all turns into 0 plus c. So that means velocity as a function of time is equal to the initial velocity, c, minus mu gt. Just switch the order of those. Part 2, we want to do the rotational one, so I'll solve this differential equation. So separating my variables, I get EW is equal to omega g over r. That's all just constants. So omega as a function of time will be equal to mu g t over r plus c. And then I'm going to use the fact that at time 0, when it first hits the friction patch here, it's not rotating at all. It's only sliding, so that means its angular velocity is 0. So that means c is 0. So that's that. All right. And C, they want us to derive an expression for the time it takes the ring to travel the distance L. Well, let's see. If we want time, I think probably we need to do something with kinematics, right? So let's see if we can do that. We know that, let's see, do I have a constant? I do have a constant acceleration, right? You can think about what's the derivative of this. The derivative of this is velocity. Well, that's what we had right back here, right? That would be acceleration is equal to negative mu g. So I have a constant acceleration, which means I can use kinematics. So let's figure out what we have. We know that acceleration is equal to negative mu g, right? We know that the initial velocity is equal to v sub 0. I don't know the final velocity, but I don't think I really need to know it right now. And we're trying to find L. Oh no, we know at the delta x, the distance it's going is L, and we're trying to find t. So it looks like that would be the equation. L is equal to initial velocity times time plus 1/2 a t squared, right? So that's the equation. Delta x is equal to initial velocity times time plus 1/2 at squared. So let's see if we can solve that for t now. Ew, that's not very, I don't like this. I don't like it. I don't like it because of those t's in there. Well, let's see if we can no, we can't. We'd have to do some kind of crazy quadratic formula thing, so there must be a different way to get to this. So the time it takes the ring to travel the distance L. Well, I'm going to have to come back to that in a minute. I'm not seeing the other way to go here. That seems like the obvious way to go, and it's not working for me. Unless, did I use the wrong? I think I used the right equation. I think I like everything there. The time it takes for neutrons. All right, anyway, I'll come back to that in a minute. I'll go peek at the answer, and then we'll fix that up. Derive an expression for the magnitude of the velocity of the ring immediately after it has traveled the distance L. So that's the condition that I was talking about here. As soon as it travels that distance L, that's when it starts doing rotating with no sliding. Rotating and no sliding means that v is now going to be equal to omega r. That's not true if you're sliding. So that means V is equal to omega r when there's no sliding. You can bet that they're going to give a point for this, for saying that. Now, I have expressions for those things. So that means V is equal to omega r. The r's cancel out, and I get what am I solving for here? Hold on a second. Oh, maybe this is what I'm supposed to do with my... Oh, I think we just figured out how to get the time. Sorry, let's take this up here. I think my variable here is time, isn't it? So here, I think I just did the wrong thing in the wrong place. It's the same thing. The time when this happens is the time when that's true. So I think it was not, in fact, kinematics. It looks like adding that to the other side, I get v sub 0 is equal to 2 mu gt, so t is equal to v sub 0 divided by 2 mu g. All right, there we go. There's that part. Okay, now that we have that, derive an expression for the magnitude of the velocity of the ring immediately after it has traveled the distance L. Now I think I can use kinematics, so I think I just had those backwards. So let's see. Part D, we want to know, derive an expression for the magnitude of the velocity of the ring. So we want final velocity. I know my initial velocity is v sub 0 when it enters that patch. The final velocity is what I'm looking for. The acceleration is minus mu g, and the amount of time it's doing that is, or I guess the distance that it's doing that, you could do it that way, is L. Right? So let's see what that gives me. So Vf squared is equal to Vi squared plus 2a L. So the velocity as it comes out of the patch of friction is going to be the square root of v sub 0 squared minus 2 mu gl. Let's try doing it the other way. I also knew from my last part that our time is equal to v sub 0 over 2 mu g. So that should have also worked. So let's get it in terms of those things instead. See how that looks. And that might also be a key to getting an expression for L, right? So let's see what that looks like. Then if we pretend we didn't know this, then we would have VI, VF, A, and T. So that would just be final velocity is equal to initial velocity plus acceleration times time. And then those cancel out, and we get that the final velocity is v sub 0 minus v sub 0 over 2, so that's v sub 0 over 2. I think that's probably what they're looking for. Although I think that's probably equivalent. Maybe they just didn't have an L in there. I wonder if we can check their rubric and see if that's acceptable. Okay, and then last we want to derive an expression for the distance L. Well, I think we could do that probably with these two expressions, couldn't we? We could set those equal to each other. So let's see if that works. Gets us anywhere productive. Square both sides of that. That would give me v sub 0 squared over 4 is equal to v sub 0 squared minus 2 mu gl. And then if I move that over here, that gives me 2 mu gl is equal to v squared minus a quarter of v squared would be 3v squared over 4. So L would be dividing by 2, that would be 3v sub 0 squared. That turns that into an 8. And then have a mu GL. Oops, sorry, I'm solving for L. So it would be that. Oops, there it is. All right, that's a pretty crazy problem. If you can beat 2.7 points, then you're doing better than average, right? And we'll take a look at the rubric for that tomorrow.